This sample problem deals with opening a door and calculating the torque, the angular acceleration, and the linear speed of the outer edge of the door, and then repeating the calculation if the person applies force near the hinge instead of near the end of the door. So that sometimes happens if there's a crash bar on a door and you're not sure which side the hinge is on. So let's go into our calculations here. I repeat the data that's given in the problem. We're using 40 newtons of force, and we're not pushing perpendicular to the door. We want to get a little practice in using a component of the force. So 80-degree angle is our angle here between the door and our direction of the force, and we're 27 inches away from the hinge where the force is applied for this first part of the problem. The door itself is 31 inches wide, has a mass of 15 kilograms, and we'll give you this data: height of the door 80 inches, and we'll see if you want to use that or not. First, calculating the torque. The torque is the force that's perpendicular to the lever arm times the distance of that force away from the axis of rotation. So, taking a look at the numbers here, we have 40 newtons. The sine of 80 degrees times the 40 newtons gives us the portion of the force that's perpendicular, the component of the force that's perpendicular to the door. This would be our lever arm then. And the lever arm is 27 inches converted to meters. You should pause and do this calculation on your own calculator. I keep an extra digit for intermediate results that we'll be using later. So 27.02 newtons per meter, we'll round off 27.0 newtons times meters. I might have said newtons per meter before, sorry. Newtons times meter is the unit of torque. And that answers part A. That's the torque that's been applied to the door by the person in this first situation. Now we want to calculate the angular acceleration of the door. Well, the angular acceleration is found by this formula, like the symbols in this Greek alphabet on this PowerPoint are not traditional, but this is torque, tau, a lowercase tau, equals capital I, the rotational inertia number, times the angular acceleration. This is the equivalent of F equals ma, but for a rotating system. Torque equals I times alpha. Well, we're going to need the value for I, and a door can be thought of as a tall rod. So we use the calculation for the rod, and 1/3 ml squared, the length of the rod. M is mass, and again, I came up with 3.09999 kilograms times meter squared. The height of the door is not important. It's only things that go outward from the hinge that are important, not the vertical. That contributes to the mass. Perhaps if you double the height of the door, you'll double the mass, and that would be given to us. But for the torque calculation, we do not have to use the data that's given here, the 80-inch high door. Well, let's go ahead and complete the calculation. The previous slide, we came up with a torque of 27.02 newtons times meters equals I, 3.09999 kilograms meter squared times alpha. If you divide both sides by the I number, and I came up with 8.72 radians per second squared, rounding to 3 digits for my answers to questions and homework problems. Then calculate the linear speed of the door. This door is rotating. What is the linear speed of the edge of the door as the rotation takes place? Well, to calculate the linear speed, that linear speed v is equal to the radius times omega. Our point of interest here is out on the edge of the door, 31 inches from the axis. So r is going to be 31 inches. We'll convert that to meters. For the omega, what is the angular velocity of the door? Well, we can use the kinematic equation. We're assuming we have a constant force at a constant angle to the door. So that'll give us a constant value for the alpha, for the angular acceleration. And then we're allowed to use omega equals omega naught plus alpha times t. So the final angular velocity after the time interval, we started at 0 angular velocity, the door was at rest, and we have a calculation of the angular acceleration times the time. Again, pause and do the calculation. So I have an omega number. Now we can calculate the speed of the edge of the door. R is here, converted to meters, and we have our omega number. I came up with 2.06 meters per second. 2.06 meters per second. That's how much space will be swept out by this edge of the door in 0.3 seconds, and hopefully that'll be far enough away here that we'll be able to walk through the opening of the door without hitting the door as we continue to walk forward. But what if we don't know where the hinge is located? Perhaps you've encountered this where you go to exit a building and there's a crash bar, not a doorknob that tells you where to apply force, but a crash bar, and you don't know where the hinge of the door is. And let's suppose this person did not know and they guessed incorrectly. They made a poor choice. And they're applying a force here only 2 inches from the hinge instead of 27 inches from the hinge. How do the numbers change? Well, I'm going to repeat all these 3 calculations on one slide. Again, the torque is the perpendicular component of the force times the lever arm. Now we're down to 2.00 Newton meters of torque. The angular acceleration, again, torque equals I times alpha. We'll divide by the I number. Now I get 0.645 radians per second squared. And what's the linear speed of the edge of the door for this situation after 0.3 seconds? Well, you plug in the numbers, and I came up with a linear speed of 0.152 meters per second. That's 15 centimeters in a second. So if you count 1001 and imagine 15 centimeters of distance forward, the door is not moving very much. The door is not moving very much, and my face is going to run into this door. Where I pushed poorly, I applied my force near the hinge. That doesn't create much torque because there's not much lever arm, and the door does not swing away from my path as fast as I would like, and I crash into the crash bar. So the point of this, apply force far away from the hinge to create a usable torque, a big torque. So if you'd like to visit more of my videos, over 500 physics and astronomy videos, I've listed them. I've annotated a list at gpclements.com, my simple website, and the annotation is a title. There's a direct link to the YouTube video. You don't have to search on YouTube. You can go directly to the video. There's a listing of how many minutes the video lasts and a description of what's being calculated. All this content is free. You're not allowed to resell it, but you don't give me your name, any information, no email address, and my website does not put cookies on your computer. I don't know how to do that anyway. So keep working sample problems. Ask your instructor if you have questions.